This session is about the introduction of Delta servo system. One is ASTA A2 and the other one is ASTA B2, which is the two main generation of the servo drives that we're promoting right now. And here is the outline of today, that we will first start with the introduction and then move on to the servo products classification, okay, and then features, specification, some applications that could be done with the servo products, okay, and we will then move on to a more practical information, like how to select the products and some accessories. And then we will have some hands-on practice, okay, which will be mainly related to our software, which is AstaSoft. Okay, so including a few topics like identifying servo info, okay, how to configure parameters, setting up some digital input output, okay, and also that how to conduct tuning. Okay, and we will see that how much time that we have till then, and then we will see that how much content that we can move forward. Okay, so let's jump right into the topic. So first of all, that what is servo? Okay, so basically that servo is a system that works as the host commands it to do. Okay, so basically that it's the motion system which is adopting the position, direction, angle of the object as the control factors to follow the target commands. So as you can see that in this indication picture, that this professor is ordering the motor to go to a certain position. Okay, then the motor should move along and arrive at the target position. Okay. So the next question is, why servo? So here are some benefits and advantages that we could achieve by using servo products. So the very first thing will be the accurate positioning. So servo products, it's quite convenient, okay, and it's very common and popular that among the applications that require accurate positioning. And there are some applications that we will see that in the end of this presentation. And then the second thing that will be high speed. So if we have a machine that's moving in a very slow speed, okay, so then it's not that difficult to achieve the accurate positioning. Okay, we can think about like a driver is trying to park his car. If we want the person to park that car in a very small space, okay, if he drives very slow, okay, then eventually that he could park his car into the right place. Okay, so which is actually, we can think about this is the same concept of servo products. However, if the objects, okay, if the car is moving at high speed and we want the car to park in a very small space, then it's very difficult, okay, or sometimes even impossible. Okay, so this is also the same for the motor, because when the motor is carrying a heavy load, okay, maybe the machine that is integrated with is quite heavy or is quite big. So then when it comes to accurate positioning, it may be hard, okay, to achieve it in high speed. Okay, however, servo motor has the capabilities to achieve it. So these are two biggest advantages that we're looking for to achieve with servo products. So one is accurate positioning, and the other one will be high speed. Okay. And then the next one will be real-time control. So as we can see that on above, that servo is a system that works as the host commands it to do. Okay, so what is very important is that when the host sends a command to the slave, okay, here we can think of a servo drive as a slave device. Okay, when it receives a command from the host, that it should respond immediately. Okay, so we can make sure that there's less delay as much as possible. Okay, otherwise that if there's always like a 1 second or even more delay that every time when the servo drive is reacting to the command, then eventually that there will be a deviation, okay, or a delay between the command and the feedback, okay. So then eventually that we will not be able to reach what we would like to pursue, which is the accurate positioning, okay. So this is why that this real-time control is important, okay, and because that servo has the ability to react to command, okay, like immediately, okay. So this is what we're also looking for. And then the next one will be the high overload capability. Okay, so when we're selecting the servo products for application, what is very important is that we need to know that for the motor, that how much power ratings that we need, okay, in order to drive the machine. We need to make sure that the motor is powerful enough. Otherwise, it might happen is that the motor cannot run the machine, and then eventually then maybe there's some alarm, okay, or even damage the products. So it means that we need to make sure that the torque generated from the motor is enough, okay. However, with higher torque, which means higher power ratings, it means that not only the dimension, but also the cost, okay, of the motor and the servo drives will increase. But sometimes that in the application, it's not necessary to have that much torque at all time. Probably that we just need more torque during the acceleration or deceleration. Okay, so maybe in a whole cycle movement, maybe this part only occupied for maybe, let's say, 20%. Okay, so if we need to have a bigger motor, a higher power rating motor, just for that 20% in the whole movement, okay. So maybe if we're talking about that cost and performance ratio is not that worth it. Okay, so in this case, then actually we may select a motor with the lower power ratings. However, with this high overload capability, that the motor can generate more torque, let's say maybe 200% or 300% in the rated torque in a very short amount of time, then it will still be enough to handle the whole system. So in that case, we don't have to size up the motor, but we can still manage the whole system properly. Okay. Okay, next one. So let's talk about the system structure inside the servo system. Okay, so first of all, okay, for sure that we need to have a servo drive, and then we need to have a servo motor with encoder. Okay, so what encoder works and that what is for that I will explain later. But basically that encoder is a device that it can use, okay, to transmit the position feedback to the servo drive, so that the servo drive can identify that which position the motor is right now, and see that if there's too much deviation that needs to be compensated, or it's actually following the command quite well and just keep on going. Okay, then the next thing is that maybe we have something like a gearbox. Okay, so gearbox that it can help to generate more torque. Okay, so if we don't want to size up the motor, so this could also be an option. And then what we will also need is some accessories. Okay, so we will need cables. So like you can see here, we have the encoder cable, okay, which is connected to the encoder, and the power cable, which is connected to the main output, okay, from the servo drive to the motor. And also that we will have connectors, okay, for different terminals, that's for different purposes. And then this is a very basic servo structure, servo system. And if we want to integrate it with more devices, then we can have something like I/O module. Okay, so we can use it to wire digital or analog input output. Okay, and also we can have some regenerative resistors. Okay, so that when the motor is breaking, okay, or if there's some unexpected high input power, that it can be dissipated through this resistor. And with this set, then what we can move on further is that we can have some peripheral devices. Okay, like we can have it connected to a PLC or motion controller. Okay, HMC, which is actually it's a human machine controller. Okay, and this is like HMI. Okay, sorry, we're missing a description here, but yeah, I believe that you're all familiar with it. So with these can all be like, think of it as a host or a master. Okay, so they're sending commands to the servo drive. So in this case, so servo drive will work as a slave device. So it will receive the command, okay, and then run the motor to the right position, okay, with the right speed. Okay. And then if we move on one more further level, then we can see that maybe we'll have a cabinet, and it's something that we will see that which combines all of the devices. So like here we have an HMI, okay, some PLC, and we have Ethernet switches, okay, and they can communicate with servo drive, sending commands, either maybe like via CANopen or like Modbus, okay, or something like EtherCAT, but sorry, it's not mentioned here, but yeah, these are all possible options. So now let's move on to Delta servo products. So as you can see that we first have our very first series Asta A in 2004, and then we keep on developing new series. So right now that's these two series, which is Asta A2 and Asta B2, are the ones that we're promoting. And then it's the product hierarchy that we can see here. We have a coordinate with the horizontal one as the encoder resolution, okay, and the vertical one as responsive ability. So if we just look at the two series that we're mainly promoting here, so we can see that A2 falls in this part and B2 is a little bit lower. Okay, so why we want to use encoder resolution and the responsive ability as the criteria to categorize our servo products. Okay, so as I mentioned previously, there are two major advantages and the purposes that we want to achieve with servo product is that the accurate positioning, okay, and the other one is the high speed. So for accurate positioning, so as I mentioned that encoder is a device that's used to read the feedback position and send it back to the servo drive. So it means that encoder, the resolution of the encoder, okay, it will directly affect that how much and how well that we can make and optimize the position. Okay, so let's say that if we have a resolution, okay, just maybe 2,500 pulse, okay, per revolution, and comparing with an encoder which has 100,000 pulses per revolution. So for sure that the encoder with a higher resolution can reach a better positioning. Okay, so this is why that we use this one as one of the criteria, okay, to categorize the servo products. As for the other one, which is the responsive ability, so responsive ability, okay, we can think of it as that how fast and how well the servo drives can react to the command. Okay, so if it can react to the command as fast as possible, it means that we have less delay, okay? And so with less delay means that it's more likely that we can achieve that reaching the right position, okay, in a very high speed, okay, in real-time control. Okay, so this is why that we use responsive ability, okay, which we will talk about it later as a term of the bandwidth, and encoder resolution, okay, as two criteria when it comes to categorizing the servo products. So here, as you can see that let's start with B2. So for B2, the encoder resolution, okay, the highest one that it can support is 17-bit, okay. And the bandwidth, okay, which is related to the responsibility, is 550 hertz. As for the power rating, it starts from 100 watts, okay, and it can reach 3 kilowatts. And as for B2, then we can see that A2 supports a higher encoder resolution, which is 20-bit here, okay. And also the bandwidth is higher, so it can reach 1 kilohertz. And for power ratings, it starts from 100 watts, the same as B2. However, it can go up to 15 kilowatts. Okay, so basically that it can be easily told that A2 is the series that is more advanced than B2. So let's take a look at this table. So this is how we classified our products. So right now, that since that we're mainly promoting A2 and B2, well, the rest of it, we're either not promoting them or either they're already phased out. Okay, so we can just focus on these two series. So first of all will be the input power. Okay, so for input power that we have two series. One is 220 volts, okay, AC, and or 380. But it's also common that you will hear people saying that, oh, okay, so we have a 200 volt series or 400 volt series. Okay, but basically that it's the same. For A2, that it supports both these input power. And if it's lower, okay, than 1.5 kilowatts, then it's single phase and three phases. Either one is possible. But however, if it's a power ratings that is equal to or higher than 2 kilowatts, okay, and keep going up, then it's had to be three phases. So this is for 220. But if it's for 380, then it's mandatory to have three phases here. And then for encoder resolution, as you know already, that is 20-bit for A2. And for the bandwidth, that it can go up to 1 kilohertz. And then you can see the digital input output and analog input output set here. And then for the post command frequency that the serial drive can identify. So for open collector, so this is the maximum that it can support. And if it's LD, which is line driver, a differential signal, then we will see that it has the higher data transmission rate. And as for the communication interface, that's for A2, that we support Modbus, which is RS-23245. We can use a USB port, to communicate with the PC, to use the software to configure some parameters. And also we have CANopen and EtherCAT, if the applications require some field bus communication. And then below the last three parts, which you can see here, is the PR mode, full closed loop, integrated ECAM. These are the built-in motion function of the Delta servo drives. So for A2, these three, they are all equipped. And then if we move on to B2, so for B2, it only comes in 220 volts AC series. There's no 400 volt AC B2, and there will not be any in the future. So basically that for the input power is the same as A2. And then for resolution, bandwidth is lower than A2. For digital input output and analog input output, you can see the number here. And then for the rest, you can have a look. And then as we can see that for B2, it doesn't come with these three built-in functions. So it doesn't have PR mode, there's no full closed loop, and also there's no integrated ECAM in B2. So overall, we can see that, as I mentioned previously, that A2 is the model which is more advanced, having more function than B2. The next one, what is, we can say that the major difference, between A2 and B2. Basically, that we can say that the difference is that one is with the built-in function, built-in motion, while the other one doesn't. So first of all, this one is B2. For B2, we will need a higher level of the host controller, because not only that the host controller needs to give it the sequence, needs to tell the servo drive that when you should execute which command. Also, it needs the host controller to create and program the command. So then the servo drive can identify which profile that it should be carrying out. So as you can see here, that all the motion and sequential commands, they need to come from the host controller. But what about A2? So for A2, because A2 itself has a capability to program different kinds of the profile command. So in this case, even we need a host controller, it just needs to switch between different commands to tell A2, which one that you should execute, then that will be enough. So in this case, only a lower level of the host controller is enough, because even the host controller, is not able to provide the profile command for A2 to execute it. A2 is still able to program by itself. So basically that you can see that the critical commands that generate in servo drive that can be handled by itself, that this will improve the performance for the whole system. So in this case, then we will see that the host controller selection will be different. And also we move the motion part from the host controller into the servo drive. So this could be could provide more options for users when selecting which products and which model that they need. So now let's talk about the main features of A2. The encoder resolution, it can reach 20 bits. It supports the communication protocol like CANopen, DMCnet, and EtherCAT. So CANopen and EtherCAT, I believe that everyone is very familiar with it. It's a very common and popular field bus protocol. Well, what is DMCnet? Well, DMCnet is a protocol that is developed by Delta itself. It's called a Delta Motion Control Network. So basically that's, this is somewhere that the transmission rate falls into the middle, But here that we're mainly promoting is the CANopen and EtherCAT type, which I will also mention later. And then for A2, for some specific models, like you can see here, like A2U and A2E, we have extension digital inputs. So in total that we can have 40 inputs. So A2 comes with a built-in motion function, also ECAM, and it can provide the gantry control. And the bandwidth, it can go up to 1 kilohertz. And we have some filters. and also that can help with the resonance suppression, okay, using some notch filters. Okay, we also have some additional function, what we call friction compensation and bumping protection, okay, to optimize the system behavior. And also we have different operating modes. We can briefly categorize into position, speed, and torque. And full closed loop control, okay, is another built-in function for A2. So now let's talk about the model name definition. Okay, because this is important that when we're helping the users to choose the model. Okay, so first of all that is something fixed, which is ASD. Okay, AC server drive, and then A2 the series, and then the 2 digits. Okay, these 2 numbers. These are the rated output power. So you can see the code here. As you can see here in this example, this is 04. It means that this is a 400 watts servo drive. And then the next 2 digits, okay, is the input voltage in phase. 2 here stands for 220 volts, and 1 stands for the input could be either single phase or 3 phases. However, if it's 3, it means that it's mandatory to have the 3 phases input. So while 2 stands for 220 volts, 4 stands for 400. So here we have 0421. Okay, it means we have a 400 watts, which the input power should be 220 volts and either single phase or 3 phases. If what we have is a 0443, it means we have a 400 watts, but 43, it means that what we have is a 400 volts and the 3 phases input servo drive. And then the last one part is the model type. So for model type, we need to have a look at the table below. So basically that we have different types for A2, like L, U, E, F, M. But since we're only promoting the E type and M type here, okay, so I gray out the rest of it. So let's just focus on E and M. So for E and M, the major difference, okay, is that E is for EtherCAT, while M is for CANopen. So you can see that we also have some differences in other specs. Like for M, we have RS-485, while E doesn't. Okay, and for extension of digital inputs, E has it, while M doesn't. And also that you can see that there are also some differences when it comes to analog inputs, okay, or post-train or internal motion functions. However, the major difference, okay, the biggest difference when it comes to selecting which model that the user should use for the application should always be the command source. So in this case, for EtherCAT, the host controller will send a command, okay, via EtherCAT. So it's important that we need to use the EtherCAT type. Also, the same principle will apply to CANopen. So first, we need to define the command source, and then we can see that what are some rest of the requirements that we can help to fulfill. And the next one is the availabilities that you may find that in our stock, okay, or what you can. So here, different model names are listed, and also the input power and the power rates are listed. You can see that we're mainly supporting that M and E. Okay, for F, we also can sell it, but however, it will be a BTO product, which means build to order. So if it's a build to order, it means that we may not have stock regularly. So if you want to order it, it means that when you ordered it, we will have to also place the order to our production line, which inevitably that lead time will take longer. So basically that we suggest to choose the one that is mostly available. And then these are the information that to explain that what are some differences that between different models, which you can also find the information in the user manual, and I will show you later. And here, just one remark to let everyone know that is that, as I mentioned, that we have higher power ratings up to 15 kilowatts for A2. However, what we have is the ASD A2R, 11 or 15 kilowatts, not ASD A2. Okay, so as you can see here, available model for 400 volts, A2R 11 and 15 kilowatts is A2R-F and A2R-M. So next page is about how we identify the serial number of the servo drive. Okay. We start with the model name here. So here we can see that this is a A2M servo drive, which is a 400 watts and 220 volts input. And then it's the power rating. And then it also indicates the applicable power range. And then it's the rated output. And then it's a very important info, which is the firmware version. Because for different model, like A2M, A2E, we have a different firmware for it. And for different firmware, it means that probably that there are some different parameter configuration or some different settings. Sometimes that when we encounter one problem in certain model, it doesn't necessarily mean that it will also happen in other model. If the users, they encounter a certain problem, but they didn't specify which model name it is. They only say, oh, okay, I have a problem with A2, but they didn't specify it's a problem with A2M or A2E, then it could lead to certain misunderstanding because we don't know which firmware version you're talking about. And then it will also cost some time to communicate with the users to understand that what is some detail. And then some time will be consumed, which will be not that efficient. So it is very important to know that which model name is it exactly and which is the firmware version. Okay. And the next one will be the serial number. So this is a very long line of the digit and the number, but I will explain it later. And here, the last is the barcode. Okay. So for serial number, so how do we interpret it? As you can see, this is the model name. Well, basically that is the same as you can see find on the top. Okay, here is A2, is A2M, front channel 220 volts input. And then the next one, the next digit. Okay, it means the production factory. T means Taoyuan, well, in Taiwan. W means Wujiang in China. And then the next two digit, here 17, means the year of production. So in 17 means 2017. And then the next one is the production week of that year, from 1 to 52. Okay, so as you can see here, this one is made in week 16, 2017. And then the last one is the production sequence of a week, okay, starting from 0001. The next one goes through to the view of the servo drive. So you have the servo drive here, you can have a look. So starting from the top is the display. We have the keypad and the LED display. And then CN1 is mainly for connecting to PLC, okay, and some I/O module terminal board. CN2 is the connection terminal for the main encoder, and CN3 is for Modbus. And then for the last CN4, it's a USB to connect it to the PC, okay, to use software to configure it. And then for CN5 is another connector for the encoder. But why we need two encoders? This is for the full closed loop, and I'll explain later. And then for CN6, okay, this is communication port. So it could be either CAN open, okay, or DMZ-NET. And the last one is the extension digital inputs. But as I mentioned, it's only limited to certain models. And then we move on to the front view of A2E. You can see that basically that it's more or less the same, but the difference is that we move the EtherCAT port, the communication port, to the right-hand side. And in EtherCAT, there's an additional function, what we call the safe torque off, which is STO. This is the safe function, okay, that is very common, widely required here in the EMEA market. If the users, they want to have a servo drive, which is with safety function, then for now, their only option will be A2E. It's not possible to use A2M or other models to achieve that. Only A2E is possible, okay, to have the STO function. And then the bird and the ground view. Okay, so from the top, we have the connection to the regenerator resistor, power input, and also motor power. And then for the bottom view, that this is the connection to control the servo motor, and also to the grounding. And the last one is the battery for absolute encoder, which we will go through that later. So encoder, as mentioned before, so it's an electrical mechanical device, okay, that can convert linear or rotary displacement into digital or pulse signals. Can be recorded, okay, and it can be read to understand that, okay, which location, position it is. Okay, and it's widely used in many kinds of the applications. So for the encoder specification, so we have two different types. One is incremental, which has a resolution of 20-bit and 70-bit, okay, and we have the other one as the absolute with less resolution. Okay. So for incremental, A2 and B2, they both support it, either 20-bit or 70-bit. However, for absolute, okay, only A2 support it. So what is an absolute encoder? Absolute encoder, basically that is a kind of the encoder that use batteries to keep the feedback position from losing due to the power loss. As mentioned before, encoder is a device that helps to let the servo drive understand that which position it is. It can establish a coordinate, okay, and it can keep the record of the position. However, this is only valid when the servo drive is in the power on status. Okay, when the power is off and it's on again, basically that the coordinates is lost and needs to be established again. There are tons of the application that is not really acceptable for this kind of a situation, that every time when the power is on, they need to reestablish the coordinate again. So in this case, what the users can consider is using an absolute encoder. Because we have an additional battery, even the servo drive is powered off, but the position, the coordinate, can still be recorded with this, with the help of this battery, so that we don't have to do what we call homing, okay, to establish the coordinate again every time we power on. So this could be a very convenient selection, but it only supports A2. For this one is the post train that we support for either A2 and B2, okay. But as we already have talked about it, so I will just skip this part, okay. And then for field bus, okay, so we support CANopen, okay. So just to let everyone know that for CANopen, we support this a very common protocol, which is we call DS301 or DS402, or you will hear people saying that maybe CIF301 and CIF402. However, for DMCnet, as mentioned, that is a protocol that's developed by Delta ourselves. It only complies with DS301, okay, not DS402. Okay, so if today that there are certain requirements that they want this CANopen with DS402, okay, then we can only support, we can only provide and promote its A2M, okay, not other products. And also we support EtherCAT as mentioned, which is A2E, the EtherCAT type. Okay, so it also supports the modes of DS402. Okay, and what needs to be noted is that what we support is COE, CANopen over EtherCAT. Okay, not SOE. Okay, not circles over EtherCAT. Okay, it's a different stuff. Okay. Okay, so then now let's have a look at the main features of B2. Okay, so for B2, that the input power, okay, it's only limited to 220 VAC. Okay, so phase it could be single phase or three phases, okay, depending on the power ratings. And the power ratings start from 100 watts to 3 kilowatts. Okay, so here are some specifications. Actually, it's more or less that very similar to A2, just the spec is less powerful. Okay. Okay, then the next one will be the Modelman explanation. Basically, that's it's very similar to A2. Okay, so I will not go through it. Okay, so we can see that we have this starting from ASD, and then model name, power ratings, input voltage and phases, and then it's the model type. Okay, so you will see it. Okay, then the next one is B2 availabilities, as you can see here. Okay, so what we have and mainly promoting is what we call the B2B. It's the very basic model. Okay, so you can see that for 220 volts and from 100 watt to 1.5 kilowatts, okay, we will keep it available for stock. However, if it's 2 kilowatts and 3 kilowatts, in this case, since that the power input is 3 phases mandatory, okay, so we will keep it as a BTO, build to order products. Okay, so let's move on. Okay, so after we go through the servo drives, then we'll have a quick go through to a servo motor. Okay, so for servo motor, we have also different input power. Okay, it needs to go with the servo drive. Okay, so it's not possible that we're using the 380 servo drive, but we're using a 220 servo motor. Okay, likewise, that it's not possible to use a 220 servo drive with 380 servo motor. Okay, it needs to go that with the same power input. Okay, so here that you can see that some of the specs. Okay, and then here's the torque and the speed that you can also find in the user manual. And then it's the shaft type. Okay, the shaft type that we provide is always with keyway and the screw hole inside. And for other options is that all of our servo motors that we're promoting here, okay, is with oil seal. However, the users can choose whether they want to have it with or without mechanical brake. Okay. Okay, and the availabilities of the servo motor. Okay, so basically that for all the servo motor here, okay, we start with ECMA, we call ECMA. Okay, this is fixed. Okay. And the next one will be the series. Okay, so first is the rated voltage and the rated speed. Okay, if it's CEFG, it means that the power input will be 220 volts. Okay, if it's JKLM, then it's 400 volts. And then it's the rated speed. So you can see that for C that, okay, it has the highest rated speed, okay, but it will slowly decrease. Okay, it's because that these motors, okay, with different models, it always stands for different inertia. So for lower inertia, okay, the rated speed will be higher, but for higher inertia, the rated speed will be a little bit lower. Okay, and then the next digit is the encoder type. Okay, so if it's 1 and 2, okay, it's an incremental encoder, but with different resolution. Okay, and if it's 3, okay, it's encoded with only 2,500 ppr. Okay, which is way less, okay, accurate, okay, than these two encoders. Okay, and if it's A, it means it's an absolute encoder. Okay, and then for the next two digits is the motor frame size, which we also say flange. Okay, so different millimeters with different codes. The next two digits with rated output power, okay, starting from 50 watts and go all the way up to 15 kilowatts. Okay, so you may find that for all these motor powers, we don't really have all the servo drive, we have the right power ratings. For example, we have it's a 750 watts and 1 kilowatt servo drive, but we don't have a servo drive with 850 watts and 900 watts. Okay, so if that's the case, okay, it's very easy. Just choose the servo drive which has the closest and the higher power ratings to control the motor. So for example, if I want to have it's an 850 watts motor, okay, then I will not choose a servo drive with 750 watts. Instead, I will choose a 1 kilowatt servo drive to control this 850 watt servo motor. Okay, so also like the same, if we have a 1.8 kilowatt servo motor, then I will choose a 2 kilowatt servo drive to control it. Okay, and then it's the shaft tire and oil seal. So here in Eminea that we only promote the shaft with R and S. And the difference is that whether they're without mechanical brake or with mechanical brake. Then for the rest it's the same because they both come in with oil seal and they have a keyway with screw hole. Okay, and then it's the last one. Last one is the shaft diameter. Okay, so it could be standard, specific shaft. Okay, we also have other models that if you're interested, then you may find more information, okay, in our documents. Okay, so when it comes to choosing the motor, okay, apart from the power ratings, apart from the sizing, some major limitation is the encoder type and the shaft type, okay, as below. So we need to see that based on the application, we need just incremental encoder is okay, or we need an absolute encoder. And for the shaft, okay, whether we need is the one without mechanical brake and with mechanical brake, okay. Okay, so here is another ECMA servo motor, okay, which we released just with in the past few years. This is a high IP protection motor, okay. So for this, you can see the model name is basically that very similar, okay, to the ECMA series that you just saw earlier, okay. However, this only applies to 20-bit incremental encoder, okay, and for the code in the front is the same as the previous slide, so I will not go through it. But for the last two part, okay, you can see that the code is different. And how do we tell what it is? Okay, it's like this. If it's YS, it means it's the high IP protection motor without mechanical brake. If it's YF, it means it's the one with brake. So you can see that we have a comparison table here. And these are also, okay, the available motors that you may order. Okay, so basically this is the same. Okay, you can just do the cross-reference, but this is for high IP protection. And for our high IP protection motor, okay, for motor itself, okay, due to the flange size limitation, the spec we have is IP65. However, for these connectors, okay, these are the IP67 connectors. Okay, so if the customers need such products, okay, they can have a look and see if we want to choose it. Okay, and we also have some gearboxes. Okay, and I will not go through the specs just one by one, just to let you know that we have one is the PA precision, and we also have the other one as the PS. Okay, so you can see that for the ratio. Okay, so PS and PA. Okay, so that there are some differences, and okay, you can have a look in the detail in the catalog. Okay, if you're interested. Okay, so now here is another topic that's I think worth mentioning is that what should we do that if there is a request that from certain users that they want to fix the Delta servo product which is already phased out, or we want to replace it. Okay, so first of all, that here are some series that we already phased out. Okay, so we have is A plus, A, B, and B. Okay, these are all series that we don't have stock and we have no replacement for it. So what can we do? Okay, we can only suggest them to change the servo set to A2 or B2. Okay, and then we also have is the phased out servo motor. Okay, so what we have now is the ECMA series, but what we don't have now is the ASMT series. Okay, so also we will suggest to use the ECMA servo motor to work as a replacement for it. Okay, and then it's the compatibilities. Okay, so it's important to know that for which servo motor can work with which servo drive. Okay, and how do we tell it? Okay, so we need to check that for encoder type, which type that do they support. Okay, so as you can see here, for these four with lighter color, okay, these are the phase out series. Okay, so you can see that for the major servo drives that we have, the servo motor, okay, for the code like 1, 2, 3, and 8, okay, for these, okay, only A plus support, okay, some of it, while the others not really supported. Okay, so in this case, it's not possible that we can use an ECMA servo motor to work with these servo drives. Okay, but if it's A2, B2, okay, or another model that we're not promoting, but it's also an existing model that which is we call the M series. Okay, okay, it's completely okay with them. Okay, to work with the motor with these encoder. Okay, so here comes another question is that, okay, now we know that A2 can support 20 bits, okay, encoder resolution, while B2 supports 17-bit encoder resolution. Okay, so what will be the final resolution if we use A2 with a 17-bit encoder motor, and instead we use B2, which is only having 17-bit encoder resolution, and have it work with a motor with 20-bit resolution encoder motor? Okay, what will happen? Okay, so the answer to this is that the final resolution will be always adjusted based on the resolution of the servo drives. Okay, so as we can see in this table, okay, so A2, although it can go up to 20-bit, it can also support 17-bit. So if today we use an encoder, which is C1, the one with 20-bit, eventually the resolution will be 20-bit. However, if we use A2 and let it to work with a 17-bit encoder, the final resolution will be 17-bit. Okay, so A2 will adjust the encoder resolution of itself to match with the actual encoder. And also, this principle applies to B2. So B2, it only has one encoder resolution to identify as 17-bit. So if it's working with the 20-bit encoder, eventually the resolution can only be 17-bit. It will not be able to go up to 20-bit. And if it's going with the same type encoder, 17-bit, then it will be also 17-bit. Okay, so what is the reason behind of it? Okay, why we always let the final resolution follow the servo drive, but not the encoder itself? Okay, the reason is that Okay, so right now, okay, just for information, that right now that Delta servo drives can only go with Delta servo motors. Okay, so far it's not possible to work with the third-party servo motor. Okay, but we're working on it. Okay, we'll have some progress, and hopefully that we can release to you soon. And the thing is that for third-party servo motor, or for any motor that we might not know, or we're not sure that the encoder resolution is, if we let the final resolution follow the servo motor, what might happen is that for the original command that we defined with the gear ratio with the host controller, it might not match the final resolution of the servo motor. So when we connect, okay, a servo motor with a different resolution, then maybe that for a machine, okay, the whole movement limitation, okay, it's maybe 10,000 pulses. Okay, so for 10,000 pulses, we can make sure that the motor will move within the range and will not damage the machine. However, if we've let the resolution follow the servo motor, and once we replace it, maybe we're still sending the same pulses, but it may exceed the limitation due to the different resolution. Then it may damage the machine. Okay, but if we always let the resolution follow the servo drive but not the motor, then we can always make sure that no matter which motor that we change, that we can make sure that the command is always within our control. Okay, so this is very important, and this is the reason that we designed it like this. Okay, so the next part will be that when there's a phase-out product, how do we replace it? Okay, so in this, let's have a look at these two flow charts. First, we have this phase-out servo drive. Okay, so if it's phase-out, we need to choose A2 and B2 to replace it. And then we need to see if the old servo motor is compatible with these two series or not. If yes, okay, then we just replace the servo drive. But if no, then unfortunately that we need to choose a servo motor to replace the old motor as well. Okay, and then the same principle applies to a phase-out servo motor. We'll choose the servo motor, ECMA servo motor, and if it's work with the original servo drive, there's no need to change it. But if not, then unfortunately we need to change it. Okay, and as highlighted here, unless there are some changes on the original mechanical system, otherwise, okay, we can always offer the products with the same power ratings. So here, as you can see, we have the AB series, which is a 400 watts, 220 volts input. And if we want to propose an A2M to replace it, then we can also propose is the one with 400 watts and 220 volts input. Okay, so yeah, okay, still has time, so let's go through this quickly. So then, now we'll move on to the section that for some specs regarding to servo drives. Okay, so this is the pulse train that we can acknowledge, okay, as a command. Okay, and you can see that we recognize AB phase, clockwise or counterclockwise, or pulse and direction. And then we also have the digital inputs, outputs with PNP and NPA supported. They come in dry contact, okay? And the user can select whether they want to use the internal 24 volts provided by servo drive, or they want to have an external 24 volts provided by their own power supply. It's also possible. And then these are the wiring diagram, okay? Then this can also be found in the user manual. Okay, the next one is that besides the physical wire digital input output, Delta servo also provides the function that user can use a virtual digital inputs output to run some simulation. Okay, so in this case that we have different parameter sets. As you can see, we have P210, P2-10, or P2-18. Okay, so we have parameters that we can assign that for which function, what kind of the function that we want to use it as a digital input or a digital output. Okay, and we can also assign it as A contact, which is normally open, or as B contact, normally closed. Okay, and how do we change it? It's quite simple. So as you can see here that if we have a look at these two, okay, so you can see that the difference is at the Z bit. Okay, so if it's 1, okay, then it's A contact, it's normally open. If it's 0, then it's B contact, then it's normally closed. Okay. Okay. And besides the digital input output, we also have the analog input output. Okay. And here's the voltage range and the resolution. And it's possible that to adjust the scaling. And so we can use the analog input, okay, to give the speed or the torque command. Okay. And also we can output, okay, this an analog voltage, okay, for monitoring. Okay. So the range is from -8 volt to +8 volt. It has a 10-bit resolution. And here are some variables that we can monitor via analog output. Okay, and then some additional functions. Okay, so for this bumping protection, okay, this is basically that to prevent that if the motor, the mechanism that is trying to keep going when it reaches a certain stopper. Okay, so in this case, we can set is the level of the bumping force and the threshold of the bumping time. So it means that when this ball screw, okay, it hit this stopper, okay, it keeps generating the force that is defined by P1-57 and it exceeds the time that is defined by P158, then it will generate the alarm, okay, to indicate that there's something wrong with the application. Okay, and what we also have is friction force compensation. Okay, so that with this force added, so we can let when the object they wanted to start from the standing still to start moving, okay, the affection will be less and also it will move faster. Okay, and then for this slide, okay, this is talking about that we have the suppression capability. So for the first one, we have is the resonance suppression. Okay, so we have 3 sets of the notch filters, okay, to suppress the resonant frequency. So as you can see here, if the signal is without applying notch filter, you can see that there are quite some vibration, it's not stable. But if we add the notch filter, okay, you can see that, okay, the spikes, okay, it's way less, okay, and then the performance will be better. Okay. And what we also have is a low frequency suppression, but this is only for A2, not for B2. Okay, so we have 2 sets. Okay, so what we have is that you can see that if we have a mechanism like this, okay, so this is going left and right in a very high speed. So because the load at the front end is heavy, so inevitably when it's moving, so this arm will start to also shake. Okay, it will start to shake that drastically. But if we apply this low frequency suppression, then we can make sure that this whole arm, including the load, is connected like really well that internally, so that when it's moving fast, that this arm will not just shake, just keep shaking, that it will actually hold still and just move as one. Okay, the next one is the full closed loop system, which is A2 only. So as I mentioned that besides the CN2 for the main encoder from the motor, we also have a terminal, which is CN5, for connecting to another encoder. So the reason is that maybe for a certain application or mechanism, okay, the mechanism maybe like a belt, it's not that rigid, okay. So the actual position, we call that the mechanical position, might be different from the position of the motor, okay. And if the servo drive doesn't know what is the deviation, it will not be able to fix and to compensate it, okay. Then eventually that the deviation will be more and more, and eventually that there might be some alarm, okay. So the purpose is that besides the main encoder, we will also add an auxiliary encoder at the end of the mechanism, and we will wire it back to the servo drive, so that the servo drive, once we activate this full closed loop function, it will calculate the difference between the main feedback and the actual feedback, and then see that how much that it should compensate. You should go a little bit faster or it should go a little bit slower. Okay, so this is what we call full closed loop. So the purpose is to reduce the impact of the backlash and efficient rigidness of the mechanism, and we can ensure the accuracy of the positioning. Okay. And this one, that for versatile PR mode, this is for A2 only. So as mentioned that before that A2 has a built-in motion function. Okay, so with this, it means that we don't have to have a higher level host controller, or we can even just discard the host controller. But still, we can able to program several different motion profile inside A2. Okay, so with this PR mode, we have, okay, PR mode, it stands for position register. Okay, so it means that without a host controller, our servo drive can still complete, okay, a complicated motion profile. So we have 64 procedures that we can be applied, okay, and we have 35 homing modes, okay, that almost all of it is complying with the homing method defined by DS402, okay. So it's easy, and also we have the different options for it. So not only that we can write it to move between point to point, position to position, we can let it run in constant speed, but also we can use this PR mode to change the parameters. Okay. And the next one is the internal electronic cam function. This is also for A2 only. So in tradition, that sometimes if we want to have a cam, then we need to build a mechanical one. Okay, then it will be that more cost, and then also that it's not that convenient if we want to change something. However, with this electronic cam, then we don't really need, okay, to build an actual mechanical one. Instead, we can just create an eCam profile, okay, which can be 720 points x maximum, okay, and then we can use it, okay, to simulate all of the movement like we can see on the left-hand side, then can easily complete it with just one servo drive and one servo motor, okay. So it's very convenient when it comes to flying shear, rotary cut, or other possible cam application. Okay. And also for A2, what we have is the position latching function. Okay, so this is capture, so that we can use a high-speed digital input to make sure that every time when this digital input is triggered, that the position can be captured. Okay, exactly. And also what we have is the position detection. Okay, and this is what we call compare. So what we can do is that first we can define a value for it, and let the servo drive start to get the readings from the encoder. And once it reaches or exceeds this defined data, then it will output, okay, a signal. And then so we can use it to move on to proceed the following command. Okay, so this can be combined with the masking function, especially for the packaging application. And what we also have is the integrated gantry control. Okay, so we can use host controller to access, okay, and some wiring, then we can control this gantry, okay, easily. And also we have is a password protection. Okay, so in case that the users don't want others to have access or change the parameter configuration, okay, it's possible to use a password to protect it. But what needs to be noted is only valid for motion parameter groups. So you can see that we have the data array. Okay, so this is mainly for keeping the motion profile, like an eCam profile or other profile. Okay, then the last part will be some applications that could be done that or have already been done that quite a lot with Delta servo systems. This that first one is the gantry control. Okay, and then also it's a very typical one like the packaging machine. Okay, and also something like the flying shear, like a tube cutting. Okay, so in this case that the cutter, okay, when it reaches certain part, then it start to cut. Okay, because this conveyor belt, okay, this object is keep moving by this main axis. So it's very important that while this cutter is cutting on this object, this axis needs to also keep moving in the same speed as this main axis. Otherwise, the cutter will be damaged. Okay, so in this case, it's very important to make sure like the position synchronization, okay, is very accurate. Okay, and then it's the filling machine, okay, which shares the same operating principle as the flying shear. Okay, so basically that, yeah, indeed, when the tube reaches the right spot, you need to lower it down to inject the liquid. Okay, and it needs to move together with the bottle, and then you need to go up, go back, and then start the next cycle. Okay, and also we have typical one is the labeling machine, okay, which is sharing the same concept. And then it's an application that it's very common that when the users that will apply flow closure control is something like this jet printer with long belt system. So in this case, since we're having a belt, so it's not that rigid. And because it's not that rigid, so there may be some position deviation at the end of the machine, okay, then the actual feedback of the motor. Okay, so in this case, then if we apply an additional linear encoder or auxiliary encoder, then with this flow closed loop control, then we can solve the problem, okay, that of the position is not being aligned. Okay, and also another application that can be done with eChem is winding machine. As I mentioned earlier, that right now, Delta servo drives can only work with Delta servo motor. Okay, so it means that the users that they might have some questions that when it comes to selecting the products. Okay, so that for which motor, then we should choose which drive or sort drive, then I should choose which motor, and then what is the cable if I only want to order the connector and make the cables by myself, then what will be the model name? Okay, so in this case that if you have the user manual, okay, that you can download that in the link that sent to you earlier, then you can find that we have appendix, okay, here. So in appendix A, this is accessories that you can find that the accessories that you can order. So including like the connectors, okay, power connectors, okay, plastic type, military type, the cables, okay, the cables with the connector, okay, and also we have its encoder connectors, okay, so for plastic and military, and also have encoder cables, okay. So encoder cables, this is for absolute type and also incremental. But as I mentioned that there are a lot of things, okay, and how can you tell and how can we know that if we need the encoder connectors or power cables that with plastic or military? So in this case, then you may refer to also, it's in here. Yeah, it's also in Appendix A. And you can find the information in starting from page 761. So here what we have is the combination table of the product selection. Okay, so as you can see that we have matched the servo drive. We have is the servo drive and the motor combination. So in this case, not only we list down the model name of the servo drive and the motor for you, which you only need to choose whether you want to have which model. That maybe I want to have a can open, then here will be M. If it's EtherCAT, it will be E. And here, if I want to have a motor without mechanical brake, then I choose R. If it's with brake, then I choose S. Okay, so not only you can know that the servo drive, okay, and the motor, the model name, you can also choose, okay, if I want to have the motor power cable, okay, without brake, then this will be the model name, okay. But if I only want to have is the connector, I will build my own cable, okay, then this will be the option for you. Okay, the same for the power cable with brake, power connector with brake, or you can choose that for encoder, okay, you can have is the incremental type or the absolute type. Okay, or if you want to make your own cable, you can just order the encoder connect. So here with this X, it means the length that you can order. Okay, so 3 means 3 meters and 5 means 5 meters. Okay, so with this table, it's not necessarily means that you need to order all of it. Instead, we just provide the possibilities. Then you will be able to select then which one that you need. Okay, so we have it not only for 220 volts. Okay, and you can see that we covered that almost all of the power ratings. And also that we have the combinations of the 400 volts series. So in case that there are some questions about how to select the right, not only the servo drive motors or cables accessories, okay, you may always refer to this and to get some idea. That's about it. And then what will be next will be some hands-on practice. So AstaSoft demonstration. Okay, so please open the AstaSoft. So once you open the AstaSoft, then you will see a window like this. Okay, so if you have already connected, okay, the server drive to your PC with the USB cable, okay, then just click on Start Auto Detect. Okay, and then it will show auto detection success. Okay, and then you can click on OK. For AstaSoft, first thing what we will do is that we need to get the parameter configuration. Okay, so first please click on this icon. Okay, here this green one. Okay, with a white P inside. This is parameter editor. Okay, so please click on it. Okay, and once you click on it, okay, then it will show okay the default okay parameter configuration. So inside the server drive, we have different parameter groups, okay, starting from P0 to P7. And you can find all of the definition inside the user manual. And the first thing that what we need to do is that we need to collect the parameter, the data from the server drive. Because actually what we have now is just a configuration, okay? So the value here, okay, might not be, okay, what is the real value inside the server drive? Okay, so what we need to do is that we need to get the data. So we will do is read here with this icon. Okay, we will read the parameters and then it will start downloading the parameters from the server. So then after that, then we will get, okay, all the info. Okay, so then we can know that some situation. So first thing is that, okay, after we get the parameter value, so what will be some steps that we need to do at the beginning? Okay, so as mentioned that we have different firmware version for the server drive. Okay, so the first thing is that we need to check that what firmware version it is. Okay, to understand that if this is the latest firmware or we need to maybe update it because it's not the latest. Okay, the first one that we need to check is P0-00 here. Okay, so this is the firmware version. Okay, and you can also find it actually on here on the top left corner. So for the server drive I have is 1.047. Okay, so this is the main version. And besides the main version, we also have is the subversion. So the subversion is what we can find here in the P500 here. Okay, so the description is reserved, but this is the subversion. And for the subversion, you can see that we have 1, 2, 3, 4, 5. We have 8 digits. Okay, but only the first 4 digits is enough. Okay, so here what we have is 0008. Okay, so we can know that for the server drive I have, this is a server drive with a firmware version 1.047 and the subversion is 0008. Okay, and then what would be the second thing? Okay, so normally that when it comes to the situation that we might need to help the users to check the parameter file, okay, most of the cases that they run into some alarm. Okay, there are some problems that they need to fix it. Okay, so in this case, then we need to check that what would be the alarm record. So for that, we need to go to the P4 group. Okay, so P4 group starting from P400 to P404. Okay, you can see that this is the fault record. It will start from the beginning, and if there's any new alarm, then it will be recorded. Then just keep going down. So in this case, we just need to look at the first 3 bits. Okay, we can ignore the rest of it. We just take a look at the first 3 bits. So the first 3 bits, okay, it's obvious that I have an alarm 013. Which might also be in your case if you have a completely new server drive. And then we know that there are some record. Okay, we can check that what could be, because maybe the user said, oh, okay, I have an over voltage alarm, or maybe I have emergency stop alarm or anything. Then we can check that this is also what is said, or maybe we can find something else. And then what could be next is that we can check that how long that the server drive has been working on. Okay, because we need to know that if it's some issue that maybe just happened that as soon as it's power on, or maybe it happened that after working for a long time. So in this case, what we can check is here, P0-08 here. This is the servo start up time. Okay, so you can see that my server has started up for 42 hours. Okay, but this only indicates the time that when it's server on. Okay, so here are some basic info. Okay, and then now what we need to do is we need to try to run the server drive and the motor. So I think you can see the demo kit that I have now. Okay, so as you can see now, what I have is AL013, alarm 13 now. So whenever that there's an alarm display on the server drive, we need to disable it. Okay, so how do we know that what this alarm is about and how do we correct it? So in this case, then what we can do and what we need to do is that we need to refer to the user manual. If we have a look at the user manual, okay, then we go to chapter 10, okay, and chapter 10, here, you will see the troubleshooting part. So first thing is we need to go through alarm 13. Okay, so alarm 13, that means that here, it means that emergency stop button is pressed. So we need to disable it. But just for information that right now, there's no any physical wired digital input in my server drive. However, there's still the alarm because that this is the default, that in the default settings of every server drive, we make emergency stop, also reverse limit, and also one more is the positive limit, forward limit. We make them as B contact. Okay, because normally that this is how these sensors should be wired. They should be B contact, not A contact. Okay, but now we're just doing internal test. We don't need it, so we need to disable it. Okay, so how do we disable it? So right now that what we have is that we are having 3 digital inputs, okay, which are being set as emergency stop, reverse limit, and forward limit. Okay, and they're set as B contact. So that's why the server drive thought that these are all triggered, and therefore it will not be possible to move it. So what we need to do is we need to disable it. Okay, so that we can move on to further testing. So what now is that we have some digital inputs that we need to disable it, and then the digital inputs, okay, here in the user manual, you can find that it starts from P2-10. Okay, if you have the user manual open, you can find it in page 390. As we go back to the ASTA stuff, you can see that starting from P2-10, we have the digital inputs. Okay, digital input 1 to digital input 8. And these are the code, okay, that we can change. And as I mentioned that we can assign different function for it. And how do we know that which function it is? Then this is something that we can refer to the table inside chapter 8 here. So table 8.1, page 576. Okay, you can find the function description of digital input. Okay, so right now what we need to do is that we need to find that which digital input is being set as emergency stop button, reverse and forward limit, and we disable it. Okay, so in this case, then those 3, okay, is here. So for emergency stop, okay, the value is 21. And then for reverse limit is 22. And then for the forward limit is 23. Okay, so it means that we need to find 3 digital inputs. Okay, and 3 of them are assigned as 21, 22, and 23, and we need to disable it. So let's have a look. So we started from P2-10, and then we go down to P2-17, and then we can see that for P2-15, P2-16, and P2-17, okay, so they are set as these 3. And as if you still remember that the Z bit, okay, is the one we can set as A contact or B contact. So as you can see now that they are all in B contact, okay, but I want to change it to A contact. So I just change this to 1, press enter. And in the meantime that you can also have a look on the display on your server drive, and then you might see the changes that, okay, so now if I change this to 121, and then you should be able to see that there's no more alarm showing that on your server drive. So let me also show it to you. Okay. So now that you should be able to see that here, there's no more alarm, okay? But if I set it back, okay, it will show the alarm again. So, okay, so for example, if I now set it as, okay, so now if I set this to B contact again, and then you'll see that there's an alarm appearing again. Okay, so if I set it back, then there's no more alarm. Okay, so basically this is also something that you can work on, okay, with the display. Okay, so after that, then there's no alarm, okay, on the server drive. Okay, so now that's what we will do is that we will move on. Okay, so just let me change the screen with you. So right now that what we need to do is we need to know that what kind of the command the server drive will be recognizing. If it's for CANopen, EtherCAT, or where you send in some analog signal, some post trend, or anything. Okay, so in that case, then what we will need to do is that we need to know that which operating mode, okay, that we should set for the server drive. Okay, so for that, okay, you can see that if we go to chapter 6 here, we have the control mode of operation. So for control mode of operation, we can see that we have different mode, and we can categorize as position, torque, and speed. So this is the different code for it. Okay, 0, 0, 1, 0, 2. Okay, and also we have the for communication. And communication is for CANopen or for EtherCAT. Okay, for demonstration, I will set the operating mode into speed mode without analog input. And then I will define 2 internal digital inputs to work as a switch. Because with 2 digital switches, then I have 1, 0, 0, 1, 1, 1, and 0, 0, which is board disabled. I have 3 status. Okay, then with 3 status, I can set 3 sets of the speed command. And then I want to trigger these 2 digital inputs, okay, to see that if the motor will work, okay, accordingly with the set speed command. Okay, so first, what I need to do is that I need to change the operating mode. Okay, so the operating mode here is P101 here. Okay, input setting of control and control command. Okay, so first I will need to set it to 4. Okay, and if I set it to 4, you can see that it says, please restart the server to enable a new setting. Okay, it's because that for all these parameters inside the server drive, there are different types. And for different types, they have different icons in the front. And here you can see that, is it a read-only? It can only be set when server is off, valid after repower on, volatile, or maybe it's parameter for 3-axis, which is not for A2M. Okay, so in this case, I need to repower on. Okay, so once I set it to 4, okay, please, okay, you should be able to hear the switch of the sound of my switch. Okay, please power off. Okay, and power on the server drive again. Then in that case, then if you click on the cell in front of these parameters, then it means that we're also reading it. It's the same operating the behavior as this one, as 3 parameters. Okay, so if I click it, okay, you can see that now it's 4. Okay, and then all I need to do is that I need to assign 2 digital input as a switch. So if I go back to the user manual, and because I need to know that which function code I need for digital inputs, so I'll go back to table 8.1. Okay, and then the switches for the digital inputs. Okay, it's 14 and 15. Okay, so it means that if I set 2 digital inputs at the function code as 14 and 15, and then if I change the status, like here, 0, 1, 1, 0, or 1, 1, then I can let them run with the command set I set with these 3 parameters, P1-9, P1-10, P1-11. Okay, so first let's set the command. Okay, so the starting from P1-9. Okay, so as you can see here, the unit is 0.1 RPM. Okay, so 1000, it means the actual speed is 100. Okay, so 270, 200. Okay, but I want to change it a little bit, so maybe I'll change it to 15,000. Okay, it means 1,500 RPM. And then for this one, I will change it to, okay, 30,000, which means 3,000 RPM, which is the rated speed. Okay, and then I want to assign is the digital input as function code. Okay, but actually using this and change is not that convenient. So what we can also do is we can use this digital IO job control. Just click into it. Okay, there's a reminder. Okay, just click on OK. And then we have the IO setup page. Okay, so first all we need to do is that we need to click on this edit DIO item. Okay, so we click on it. Okay, and then we can set at which digital input we want to use. So in this case, then I will set this as digital input 2. Okay, and I'll set it as one of the switch, A contact. Okay, not B contact. Okay, A contact and click on OK. And then for DI3, I'll set this as a little bit. Yeah, I'll set it as 15. Okay, another switch for digital input. Okay, and now then it's done. Okay, so what will be next is that I can change these two digital inputs, the status on or off, okay, to run the motor. But the very important thing that first we need to do is that we need to servo on the motor. Okay, there are quite some terms. You'll hear servo ready, servo enable, servo on, or motor ready. Anyway, the idea is to let the servo drive generate a current, okay, to start having control of the motor so that it can react to the command anytime. Okay, so first of all, that what we need to do now is we need to control these digital inputs virtually. So we need to take on these boxes. Okay, so now if I click on this servo on, you should hear the magnetizing sound. Okay, and once you hear the magnetizing sound, and it means that the motor is in control. Okay, so now as you can see that I am not servo on, I'm not in this status, so I can rotate this motor easily. Okay, but now once I servo on, you can see that, okay, I'm not pretending. Okay, it's really that I'm not able to like rotate this motor that much. Okay, this is because that's the motor is in control. Okay, so what I would do now is that once this is servo on, okay, I will trigger this digital inputs to run a motor. Okay, so now let me switch it back again. I can trigger these digital inputs, and then the motor will run different speed. Okay, I think that you should be able to hear the sound. Okay, that the motor is rotating, but you can also try it on your side. Okay, so now as you can see that the motor is rotating. Okay, so now I disable all the digital inputs, so it's off. Okay, so now enable one, then it's moving. Okay, I disable this one, activate another one, it run different speed, and then I enable both of them, then it will run, okay, in 3000 RPM. But the question is that how do we know if the motor is rotating really as the speed as we expected? Okay, so then this is when that's the scope of our software will come in handy. Okay, so in this case, that you can see that we have a scope function here. Here, okay, we have a scope function. We can click into it, and you can see we have 4 channels. So channel 1 and channel 3 are one set. 2 and 4 are one set. Each set is 32 bits. So if I tick on the 32 bits, another one is disabled. Okay, so I can choose 2 16-bit or 1 32-bit. And here are some data to be monitored. Okay, so when will you use 32-bit? Okay, unless we're monitoring the position. Okay, otherwise we can use 16-bit is enough. Okay, for 32 bits necessary for the position, otherwise it will be reset. Okay, so first thing is that I want to monitor is the speed command. Here, speed command, RPM. Okay, and then I also want to monitor is the motor speed. Okay, here, motor speed, real time. Okay, and then I also want to see that if they're changing accordingly of the DI status. Okay, then the last one, okay, I don't want. And then I will just run the scope, and then I will go back, and I will try to just trigger, okay, randomly. Okay, I'll just trigger randomly, and then I come back to the scope. Okay, and then I stop it, and then I got the signal, okay, that I monitored. So For this signal, the scale is not adjusted yet. So what we can do is that we can click on this green icon. Okay, we can show all data in screen and adjust the maximum and minimum value automatically. Okay, so when we click onto it, okay, it will be easier to tell. And then we can click, okay, drag and drop, then we can zoom in, okay, to the area we want to check. Okay, but here we'll see an overview. So for the yellow one, this is the command from the servo drive. And the white one is the actual command of the motor. The green one is the status. Okay, you can see that digital input 1, 2, 3, 4. Okay, so let's see here. In this section, when it's servo on, only the first digital input is on. And then you see that only digital input is on. And then you can see that the speed should be 100. And the actual speed is also around 100. And if we enable both digital inputs, and then you can see the speed, okay, will go up to 3000. Okay, and then if I disable one digital input, okay, and only leave one on, and then you can see that the speed will change to 1500. Also, the actual speed is also changing. And then if I disable all of it here, you can see that there's no more speed coming, and also the motor is stopped. Okay, and once I change it, then it will also move. Okay, so this will be some simple test, okay, that we can use some registered digital input to run the motor, and we can use scope then to check that if the behavior is as expected. Okay, when it comes to troubleshooting, or maybe that we want to check if the behavior is as we expected, what is very important are two things. One is the command and the feedback. And for command and feedback, we have is the position and the speed. Okay, so this is one of the data we can check for the command speed and target speed or the feedback. And also what we will also check sometimes is that we will check the command position, impulse user unit, or the feedback position. Okay, but in this case, as I mentioned, since we're monitoring the position, it's necessary to take on this 32-bit. Otherwise, that the data will be reset. So then we will not see the line just going up. Instead, we will see it going up and then down, being reset, and then up and reset. So for some basic troubleshootings, then what we can do is that we can check the command and feedback position. Okay, and also the command and the feedback speed. And then for tuning, okay, why we need to do the tuning? So tuning basically is to let the servo drive know that how much load, what's the mechanism that it's driving. So if we don't know it, maybe the system cannot control the mechanism properly. Then maybe there will be some vibration, noise, or like other things that is bad for the performance. So what we're going to do is that we are going to do the tuning with this. Here we have this auto gain tuning. Okay, so this one with the gear icon. First, we click into it. For the people who are experienced with tuning, then you can just follow what you're used to do. But I also share it that maybe some method from our side is that first you can see that we have is the inertia ratio and the bandwidth. So for inertia ratio, this will be best if we can calculate it when we're sizing. But if not, okay, we can give it an estimation. Okay, so like here I have a disk, maybe, I don't know, it's like almost no load or maybe bad connection 1 or 2. Okay, but here maybe I just assume it as 2. And for bandwidth, higher bandwidth means higher responsive. Okay, but it's not always good to set it as too high. And also, especially not to a system when we're not sure that how it can respond to the command. So first, maybe I'll set it as a lower value, let's say 40, okay? Then I'll click on compute. I'll get these PID control data parameters, and I download it into the servo drive, okay? And then I enable the gain control panel. Okay, and then first I need to servo on, okay? And then the jog speed, I'll set it at 200. Okay, please be noted that the speed cannot be lower than 200. Otherwise, it's not possible to move it. Okay, then I download it. Okay, then I use this arrow, okay, to move it to certain place. And I set it as position 1. I move it back to certain position and I set it at position 2. Okay, I let the time interval be 500 milliseconds. Then I let it start to run. Okay, you can see that the inertia ratio will start to change. Once you notice that it stops changing a lot, it becomes stable, then what you can do is that we will stop. Okay, it's still changing. Okay, but I want to say sometimes, so I'll just stop. And then this is the estimation I get from the servo drive. I'll set it to panel, and then you can see that it also set the bandwidth. Okay, what it thinks that is following this inertia ratio. Okay, then I compute, and then I download it again. Okay, then this is one cycle of the very basic tuning procedure. Okay, but what we can do more and what will be also better that in the actual application is that we might need to increase the speed. Okay, so we don't have to increase to like 3,000 or more. And it's not really necessary to increase to the maximum speed that will be used in the application. Okay, but it'll be better to increase a bit because then we can try to trigger the characteristic point of the machine. Okay, so that maybe this time I'll increase it to 700. Okay, I download it. I remain in the same position, and then I start to run. Okay, and you can also try it on your side, and you can see that there might also be some changes. Okay, so just give it a while. Okay, maybe a couple of minutes or okay, and then we stop it. We set to panel, and then you can see that it's changed again. Okay, then we will compute and get back to this. Okay, so basically that we will repeat this cycle. Okay, we will repeat this cycle, and then when we reach a higher speed, but the inertia ratio is not changing that much, we can use that inertia ratio, okay, and see if we want to increase the bandwidth a bit or lower the bandwidth a bit. Okay, and then we get the value, we download into the servo. Okay, so this is a simple way for tuning. So since bandwidth is related to how well the servo motor can react, the servo drive can react to the command. So what will happen that in the actual situation, or that what we can expect? Okay, so first of all, that I think we can give it a try is that now I set the bandwidth to a higher value. I say 100. Okay, I compute servo on. Sorry, I download into a servo drive, servo on, and then let me show you the screen. The bandwidth I set it at 100. Okay, and you can see that I could not really move the motor. Okay, so now if I change the bandwidth to, if I servo off first, okay, now I servo off. And now if I change the bandwidth to 30, okay, I compute, I download into it, and then I servo on again. And you see what will happen. You can see that the servo drive is still controlling the motor, but I can move it already, okay? So this is how the bandwidth will affect the servo drive and the motor, because for higher bandwidth means that the following will be better. So even though that we're not giving any command to move the motor, but actually the servo drive is commanding the servo drive to the motor to stop at that point. So actually it's still controlling the motor. So with higher bandwidth, it means that it can also resist to the external force better. And that's why that when I try to move it, it's not possible. But if I lower the bandwidth, then it will be possible to do it.